Every 3 seconds worldwide, a new engine block rolls off the production line, the heart of a car that will withstand millions of explosions, temperatures over 4,600 degrees, and operate for decades without stopping. But how do you transform molten metal into a perfect mechanism with precision down to a micron? One mistaken dimension, and the engine will tear itself apart within minutes of operation. Every year, over 100 million of these blocks are manufactured, and each one goes through a hellish birthing process. Molten metal at 5,400 degrees, sand molds that self-destruct, and robots that cut channels thinner than a human hair. But there's one secret the manufacturers don't talk about. A mystery hidden inside every block that determines whether your car will go 60,000 miles or 600,000. Stay until the end. What you'll learn will forever change how you see what's happening under your car's hood. Let's start by understanding what an engine block actually is. It's the foundation that holds the entire engine together. Inside it are the cylinders where fuel combustion occurs, pistons that move up and down, and other critical components. The engine block must be strong, lightweight, and resistant to high temperatures. That's why manufacturing it is a complex process that demands precision and advanced technology. Everything begins with an idea. Engineers develop a concept for an engine that must be powerful, economical, and environmentally friendly. They use specialized 3D modeling software to create a digital model of the block. This allows them to account for every detail and test how the engine will perform under various conditions. Engine blocks are made from different materials, but the most common are cast iron and aluminum. Cast iron is strong and resistant to high temperatures, but heavy. Aluminum is lighter and dissipates heat better, but less durable. Sometimes composite materials or alloys are used to combine the advantages of both metals. After the engineering team completes all calculations, computer modeling, and finally approves the design of the new engine block, the true heart of the future automobile, the most interesting part begins: its birth in metal. The first and perhaps oldest step in metallurgy is casting. A massive shop filled with the hum of machinery, the smell of molten metal, and the glow of high temperatures. This is the foundry, where engineers' dreams become real components. First, a mold for the block is created. There are two main approaches to creating these molds, each with its own advantages. The first, and most common for large-scale production, uses sand molds. This is an amazing, though traditional method. First, they make a pattern of the future engine block, usually manufactured from wood or metal, and it's an exact copy of the block, but accounting for certain features, such as compensation for metal shrinkage during cooling. Then this pattern is placed in a special container, where it's tightly packed with a mixture of quartz, sand, clay, and organic binding agents. This mixture is compacted, then baked or chemically hardened, creating a strong but porous mold. After this, the pattern is carefully removed, leaving a cavity that precisely matches the shape of the future block. The most challenging aspect of sand molds is creating internal cavities, coolant channels, oil passages, cylinder bores. For this, they use so-called cores, separate elements, also made from sand, that are inserted into the mold. After pouring the metal and cooling, the sand is easily removed, leaving the necessary internal channels. The advantage of sand molds is their relative affordability per unit at large volumes and the ability to create very complex internal geometries. The second method, often used for aluminum blocks or smaller production runs, uses metal molds or permanent molds. These are stronger, reusable molds made from steel or cast iron. They're more durable and allow for parts with smoother surfaces and higher dimensional accuracy right from the casting stage. However, metal molds are much more expensive to manufacture, and it's harder to adapt them for creating the very complex internal channels found in engine blocks. Therefore, they're often combined with sand cores for internal cavities. The chosen material, cast iron or aluminum, is melted in a furnace at high temperature. For cast iron, this is typically over 4,600 degrees Fahrenheit. For aluminum, around 3,000 degrees. In massive induction or arc furnaces, metal scrap and pure ingots slowly transform into a glowing, liquid mass that shines bright orange or silvery light. This process includes precise control of chemical composition. Metallurgists add special alloying elements, such as silicon, magnesium, copper, in strict accordance with the recipe to give the future block necessary properties: strength, wear resistance, lightness. The molten metal is constantly stirred and goes through refining processes to remove unwanted impurities that could reduce the quality of the finished part. Finally, the climax arrives: pouring. The molten metal, radiating intense heat, is carefully transferred from the furnace into special ladles, then into the prepared molds. This is the moment of maximum concentration and precision. The metal must fill every cavity of the mold, displacing air and completely matching its configuration. The pouring process can be gravitational, meaning the metal simply flows under gravity or under pressure, which ensures better mold filling and reduces porosity. After pouring, the mold remains for some time, so the metal can cool and solidify. This can take from several minutes to several hours, depending on the block size and metal type. When the metal has cooled and fully crystallized, the next stage occurs. The mold is broken apart. If it's a sand mold, it's simply destroyed using vibration or hydraulic hammers, freeing the newly created metal object. The sand is later collected and partially recycled. If it's a metal mold, it's opened, and the finished block is carefully extracted. As a result of this process, we get what's called a rough engine block. It's not perfect yet. Its surface is rough, it may have sand residue or so-called flash, small metal overflows at the mold seams. It doesn't yet have mounting holes, and it lacks the micron tolerances required for engine operation. But it's already a real block, massive and heavy if it's cast iron, or surprisingly light if aluminum, but already with a clearly defined shape, ready for the next processing stages that will transform it into a high-precision part capable of withstanding incredible loads inside the engine. Mechanical processing is performed on specialized computer numerically controlled machines. The large, solid block is secured on a special table. Around it, various tools move, performing their work. Like a scene from some movie, isn't it? Let's start with the most obvious: cylinder bores. These holes must be perfectly round, have precise diameter, and be positioned exactly on one axis, since pistons will move within them. First, machines use large end mills to roughly remove material, creating preliminary holes. It's like carving out a large chunk from cheese. Then more precise tools come into play. Special boring cutters are used, which carefully remove the thinnest layers of metal, bringing cylinder diameters to the required size. This happens in stages, with constant dimension control. After this, cylinder walls undergo honing. This is final abrasive processing that creates very fine, cross-hatched scratches on the internal surface. These scratches retain lubricant, ensuring perfect lubrication of piston rings and minimizing friction, which is critically important for engine efficiency and longevity. Actually, the cylinder surface after this processing feels perfectly smooth to the touch, but under a microscope has the perfect structure for retaining an oil film. Next, oil and cooling channels. These systems that penetrate the entire block are vitally important. Oil channels deliver lubricant to all moving engine parts, such as the crankshaft, camshaft, pistons, ensuring their lubrication and heat removal. Cooling channels circulate coolant, removing excess heat generated during fuel combustion and maintaining optimal engine operating temperature. The internal, complex labyrinths of coolant and oil channels, as we mentioned, are formed during the casting stage using sand cores. But after this, they need to be opened and brought to perfect condition. For this, high-precision drills and mills are used to create inlet and outlet openings for these channels, and also connect them with other engine parts. Each hole must be positioned with millimeter, or even micron precision, so fluids can circulate freely. In a world where every second counts, water produces over 50% of all clean energy on the planet. But have you ever wondered what price nature pays for this power? To build one hydroelectric plant, you need more concrete than for 10 skyscrapers. And the river has to be stopped. Its flow gets diverted into a tunnel. The riverbed gets dried out, and a foundation is poured that can withstand the pressure of thousands of tons of water. But behind every such structure lies not just engineering, but also mystery. By the end of this video, you'll discover how water becomes electricity that powers entire cities, and what dangerous price humanity pays for controlling a river. A hydroelectric power plant is where water transforms into electricity. The river's flow gets directed through turbines that spin and generate electrical power. It's a clean energy source with zero carbon emissions, and it works 24/7. But to make this possible, you need to build a dam, a massive structure that holds back the river, creates a reservoir, and controls water flow. The first and most crucial stage of hydroelectric plant construction is site selection. Engineers carefully study the terrain, geology, and hydrology of the region, looking for a narrow section of river with solid, stable banks. The ideal option is a natural gorge between mountains, where water already has significant elevation drop. This reduces the amount of earthwork needed and ensures powerful water pressure on the turbines. At the same time, it's important to have populated areas nearby that need a stable electricity source. The closer to the consumer, the lower the transmission losses. Such location also simplifies construction logistics, material delivery, equipment operation, worker housing. Site selection is a balance between natural conditions, technical capabilities, and human needs. This is where the foundation of future energy infrastructure gets laid. Before starting hydroelectric plant construction, you need to tame the river itself. Its flow gets temporarily redirected into a specially created bypass channel, or tunnel that's built alongside the future dam. This is a complex engineering operation that allows drying out the section where the main structure will be built. Working in the dry is critically important. Concrete work, rebar installation, and foundation work are impossible underwater. Such a river bypass can function for several months or even years while construction continues. After completing the main work, water gets returned to its new channel, now through turbines that start producing electricity. Once the river is diverted, builders move on to preparing the base, the foundation of the future dam. First, they carefully level the ground, remove unstable rock formations, compact the soil, and reinforce it with special materials. Then, concreting begins. They pour thousands of cubic meters of reinforced concrete, layer by layer, creating a monolithic structure. This foundation must be incredibly strong. It withstands not only the massive water pressure, but also possible earthquakes, seasonal water level fluctuations, and decades of operation. A mistake at this stage means disaster risk, so quality control here is maximum. They use laser levels, geodetic sensors, and every batch of concrete undergoes laboratory testing. From this very foundation grows the giant wall that changes the landscape and energy map of the region. The type of construction depends on local terrain and river characteristics. If the banks are solid and located close to each other, they choose an arch dam that transfers water pressure to the side rocks. If the river is wide and the terrain is flat, they build a gravity wall that holds back water with its own weight. In any case, it's a gigantic structure. Height can reach 984 feet, and length can span several hundred yards. For its construction, they use tens of thousands of tons of concrete, delivered by conveyors, mixers, and sometimes even cable cars. Work continues for years, often non-stop, day and night. Hundreds of people work on site. Concrete workers, welders, surveyors, installers. Every stage requires precise coordination because a mistake can cost millions. The key stage of converting water into electricity happens in the lower part of the dam, where hydro turbines are installed. These are massive metal structures with blades resembling giant fans. When water from the reservoir gets directed downward under high pressure, it passes through the turbines, forcing them to rotate. This motion transfers to generators, devices that convert mechanical energy into electrical energy. A generator consists of a rotor and stator. When the rotor spins, electric current emerges in the magnetic field. All this happens with incredible precision. Even a small balance disruption can stop the system. To ensure stable operation, turbines get regularly serviced, cleaned of sediment, and temperature monitored. The result is powerful electricity that enters the grid and powers cities, factories, schools. Right here, in the depths of the concrete wall, the energy that drives the modern world is born. When all main structures are completed, foundation, dam wall, turbines, and generators, comes the moment of returning the river to its new channel. Engineers block the bypass canal, and water again gets directed toward the dam, but now in a controlled manner. It begins gradually filling the reservoir that formed behind the concrete wall. This process isn't quick. To avoid sudden level changes that could damage the structure or cause landslides, filling happens in stages. Sometimes this takes weeks or even months. Meanwhile, they monitor bank conditions, water levels, wall pressure, and turbine operation. When the reservoir reaches optimal level, the hydroelectric plant enters normal operation. It starts steadily producing electricity that enters the grid. To build one dam, they use enough material to construct 10 modern skyscrapers. This isn't an exaggeration. Concrete gets poured in layers, day and night, thousands of tons at a time. It's delivered by conveyors, mixers, barges, sometimes even cable cars. Such volume is needed to create a monolithic wall capable of restraining a river. But concrete is only part of the story. Water held back by the dam exerts colossal pressure. On every square foot of wall, dozens of tons of force. It's like several trucks pressing simultaneously on a door-sized area. Such pressure doesn't just affect the structure, but also creates potential for energy production. The greater the water drop height, the more energy can be obtained. Water flow gets directed through turbines that spin and drive generators. All this without burning fuel, without emissions, just nature's force. One large hydroelectric plant can provide electricity to millions of people. That's schools, hospitals, factories, neighborhoods, entire cities. In some countries, hydropower is the main electricity source, stable and ecological. When they build a dam, the river stops flowing freely. It gets restrained, redirected, accumulated. This changes the landscape. Valleys, forests, fields get flooded. Dozens of square miles of territory where people once lived, trees grew, and animals ran can end up underwater. Sometimes entire villages need relocation. Roads, bridges, and cemeteries need moving. It's a painful process requiring social support, compensation, and careful planning. At the same time, the river's life changes. Water flow becomes controlled, affecting fish accustomed to seasonal migrations. For example, salmon or sturgeon can lose access to spawning grounds if special fish passages aren't provided. Channels or ladders that fish can use to bypass the dam. Without them, populations decrease and sometimes disappear completely. Water's chemical composition also changes, along with its temperature and oxygen levels. In reservoirs, water stagnates, which can cause algae blooms or death of some species. The region's microclimate changes. It becomes more humid, fog appears, wind patterns shift. That's why modern projects try to minimize ecological damage. Engineers work together with ecologists, hydrobiologists, and geographers. They create fish passages, plant new forests, relocate rare species, and form artificial islands for birds. In some cases, they even create new ecosystems, wetlands and floodplains that compensate for losses. A hydroelectric plant is a powerful source of clean energy, but it shouldn't be a source of destruction. Balance between technical progress and nature is the main challenge of the 21st century. And this is where new construction ethics are born. not just to build, but to preserve. Every year, humanity produces over 4 billion tons of concrete, more than any other material on the planet. It's what our cities, bridges, and roads are built from. But every crack is like a tiny timer ticking toward destruction, started the moment water seeps inside. Now imagine concrete that actually lives, breathes, and heals itself. No people, no repairs. Deep in labs across the Netherlands, USA, and Japan, a game-changing material is being born. Inside it, bacteria or microcapsules that can seal cracks on their own, just like skin healing after a wound. How is this even possible? How did a lifeless material gain the ability to regenerate? Stick around until the end, and you'll find out how scientists brought concrete to life. Self-healing concrete. Sounds like something out of a sci-fi movie, but it's already here. Scientists invented it to solve one of construction's biggest headaches: cracks. Regular concrete starts drying out and cracking over time from temperature swings, moisture, or just plain stress. And a crack isn't just a scratch. Water gets inside, the rebar starts rusting, the structure weakens, and eventually, you're looking at expensive repairs or even a collapse. That's why researchers decided to create concrete that can patch itself up, no human help required. Sounds crazy, but it's actually pretty logical. There are two main technologies that make this possible: microbiological and mineral. The first one uses real living organisms. So-called bioconcrete was developed by Dutch researchers, and the principle is pretty straightforward. They add special bacteria to regular concrete mix, usually Bacillus pseudofermis or Bacillus conii. These bacteria can stay dormant for years, like seeds in dry soil. Along with the bacteria, they add nutrients, usually calcium lactate. And while the concrete stays intact, the bacteria just sleep. But when a crack forms and moisture gets in, they wake up. That's when the real microscopic work begins. The bacteria start consuming the nutrient substrate and, through their life processes, produce calcium carbonate, basically the same mineral that makes up seashells and limestone. That's what seals the crack from the inside, like the concrete is fixing itself. The results are impressive. Micro cracks up to 0.03 of an inch can disappear completely within a few weeks. And all without human intervention, purely thanks to nature that's been built into an artificial material. The second technology is less alive, but no less impressive. Instead of bacteria, it uses chemistry. Tiny capsules are added to the concrete, containing an active substance inside. For example, epoxy resin or sodium silicate. These grain-sized capsules are evenly distributed throughout the mix. When the concrete cracks, some of the capsules burst too. The substance inside comes out, fills the crack, and hardens on contact with air or moisture. The result is the material literally heals itself. It's similar to how certain car paints can heal scratches with heat, except this process is way more complex and large-scale. The advantage of this approach is that it works even in dry conditions, where bacteria might not activate. The downside is cost. Creating the capsules is more complex, so this concrete is pricier. But when you calculate the cost of repairing bridges or tunnels, it becomes clear. The payoff is huge. Interestingly, these technologies don't cancel each other out. Some companies are experimenting with combining biological and chemical methods to create concrete that could self-heal under any conditions: underwater, in the desert, or in freezing cold. Testing shows that structures made with this concrete last 2 to 3 times longer than regular ones. Bridges, roads, dams, parking garages, all of this can be made nearly eternal. For example, the Netherlands already built a lakeside lifeguard station using bioconcrete, and after several years, it hasn't needed any repairs. The idea is spreading fast around the world. In the US, these materials are being tested in bridges, in the UK, in sidewalk paving, and in Japan, even in concrete for coastal reinforcements that have to withstand salt water. Regular concrete, even the highest quality, has a shelf life. roughly 50 years. After that, cracks start appearing, water penetrates inside, rebar rusts, and the structure gradually weakens. Self-healing concrete changes these rules. Thanks to bacteria or microcapsules, it can heal microdamage before it becomes a problem. That's why the service life of structures can nearly double, from 100 to 120 years. That means one bridge or building can stand for 2 human generations without major repairs. Sure, this material isn't cheap yet. It costs several times more than regular concrete, on average 3 to 5 times more. But if you look at the long game, it's totally worth it. Maintaining, repairing, and restoring structures costs governments and companies millions of dollars every year. Self-healing concrete cuts those costs to a minimum. Basically, it's like buying a car that changes its own oil and fixes its own brakes. Expensive upfront, but then smooth sailing and economical. The Netherlands became the real home of self-healing concrete. Right here, at Delft University of Technology, the idea emerged to add living bacteria to the mix that could repair concrete from the inside. The man behind this idea is Dutch microbiologist and engineer Hendrik Jonkers. Nature inspired him. He noticed that certain bacteria can survive in limestone rock and create mineral deposits, filling micro cracks in stone. That's when Jonkers asked himself, if nature can heal stone, why not make concrete that does the same? In the early 2000s, he started experiments with different bacterial strains, looking for ones that could withstand concrete's alkaline environment and stay viable for years. After numerous trials, the best candidates turned out to be Bacillus pseudofirmis and Bacillus conii, spores that can sleep for decades and activate only when moisture appears. Jonkers added them to concrete along with a food source, calcium lactate. The results were mind-blowing. When the concrete cracked, the bacteria woke up and produced calcium carbonate, which sealed the cracks like natural glue. Jonkers called his invention bioconcrete, and soon the whole world was talking about it. Later, Delft University launched a project to test bioconcrete under real-world conditions. In 2015, the Netherlands built the first lakeside structure using this material. Years later, it remained in excellent condition without any repairs. Now Jonkers' lab is working with construction companies and governments from other countries, perfecting the formula to make it cheaper and more accessible. The USA and UK bet on the mineral technology for self-healing concrete, which doesn't require living organisms, but works through special microcapsules with healing substances inside. These countries are actively investing in research on materials that can automatically restore minor damage without human involvement. The principle is pretty simple, but looks impressive. Capsules or microcapsules filled with special gel, epoxy resin, or sodium silicate are added to the concrete mix. When the concrete surface stays intact, the capsules preserve their contents without reacting with the environment. But as soon as a crack appears, the capsule ruptures and the liquid flows into the damaged zone. On contact with moisture or oxygen, the substance hardens, gluing the crack edges together and returning the structure's original strength. These systems are currently being tested in US Army labs and British research centers, including Cambridge University. In the UK, they're even building experimental road and bridge sections with this material to track how it behaves under rain, vibrations, and temperature swings. American experts went even further. They're experimenting with capsules that can activate multiple times. Inside these capsules are microgels that not only fill cracks, but also expand on contact with water, creating a hermetic barrier against corrosion. This is especially crucial for bridges and skyscrapers in coastal cities, where concrete constantly faces moisture and salts. Test results show that cracks up to a few hundredths of an inch wide can seal themselves in less than a week. And if the damage is larger, the process takes longer, but still happens without human involvement. Such technologies can significantly extend the service life of roads, tunnels, and even military structures, which is especially valuable under extreme loads. In every second of our lives, there are metals we don't even suspect. Without them, there would be no smartphones, electric cars, or even jet aircraft. And now imagine a place where, in the middle of the desert, under the scorching California sun, the United States creates a strategic resource of the future without a single pound of Chinese raw materials. Here, at Mountain Pass, they mine 43,000 tons of rare earth metals annually. Rocks that look ordinary are transformed into materials for lasers, engines, and defense systems. But there's something almost no one knows about. And if you watch till the end, you'll understand why this dust from the desert can change the world. Today here, in the dust and heat, MP Materials Company mines 43,000 tons of rare earth concentrate per year, all without a single pound of Chinese raw materials. For a country that for decades depended on imports from China, this is a strategic breakthrough. The main star of this place is basnasite, a mineral that looks like an ordinary stone, but contains treasures inside: lanthanum, cerium, neodymium, and praseodymium. These very elements give life to modern magnets, lasers, electric cars, and jet aircraft. Everything begins in the depths of the quarry. Huge excavators and 300-ton trucks carry rock to the crusher. Next comes the flotation process, similar to a magic sieve. Crushed ore is mixed with water and special reagents. All this turns into foam, and basnasite particles float to the surface, while waste settles to the bottom. After flotation, basnasite goes for chemical expertise. In MP Materials laboratories, it's transformed into concentrate, and then into individual elements. This is a complex sequence of extractions and washes, where each metal chooses its own path. Once, this stage was performed in China. Now the United States is gradually building a full production cycle, from ore to finished magnets. Thanks to this, the country has already replaced 80% of its former imports from Asia, and this is just the beginning. It sounds like science fiction, but it's a fact. 2 pounds of cerium can become material for optical lenses of laser systems in military equipment. Other elements, like neodymium, are used in powerful magnets of jet engines and in missile guidance systems. All this means that every ton of ore from Mountain Pass isn't just raw material. It's a piece of American defense independence. The California desert isn't just scorched by the sun. It's politically charged. Mountain Pass is a symbol of a new era where technology and geopolitics merge. Today, American engineers, in hard hats and safety glasses, are literally building their own supply chain of the future, step by step displacing the Chinese monopoly. Just as in the 60s, when the United States first launched a satellite, now they're trying to be first to build an independent rare earth elements industry. And it all starts right here, among the sands, where it was once quiet, but now machines rumble, and the fire of smelting furnaces glows. If you gather all the rare earth elements mined here per year, it's 43,000 tons of concentrate. Outwardly ordinary dust, but actually strategic raw material, more valuable than gold. And if this dust were transformed into finished products, it would power more than 100,000 electric vehicles, those that race without a drop of gasoline thanks to neodymium magnets in motors. The same metals would ensure the operation of hundreds of guidance systems for F-35 fighters, where precision depends on microscopic lasers and sensors. And also, tens of thousands of medical lasers used for eye surgeries or to stop bleeding in military hospitals. The irony is that Mountain Pass isn't a megapolis or a Silicon Valley laboratory, but a patch of land in the middle of the desert. But it's precisely this place that's becoming a PowerPoint again. Every kilogram of cerium mined here is a potential lens for lasers in defense systems. Every gram of neodymium is a piece of an engine for an electric car or satellite. It's worth talking separately about cerium. Cerium isn't just another metal on the list of rare earth elements. It's one of those that sits quietly beneath the surface of technologies, but without it, the modern world would look completely different. Imagine a desert quarry, drilling rigs, machine cries, and dust. And among all this, under sand and stone, hides a complex chemical actor that transforms from an ordinary mineral into a material that affects aircraft, phones, and even medicine. In appearance, an ordinary grayish powder, nothing special. But this is a true alchemist among metals. Without it, there would be no clean glass in telescopes, no shine in smartphones, no precision of lasers, and no cleaner air from automobile exhausts. 1 gram of cerium can do what other materials can't even in hundreds of times larger quantities. Cerium is a true master of transformations. In catalysts, it behaves like a chemical chameleon. It intercepts and releases oxygen, converting harmful gases into harmless ones. In glass, it extinguishes ultraviolet light, makes lenses transparent as crystal. Its oxide polishes phone screens, cameras, optical devices, literally erasing microscopic scratches from surfaces to perfect smoothness. Among workers at the plant, there's a joke. Without cerium, the world wouldn't shine. And there's truth in this. Because when it gets into engineers' hands, everything around starts to shine. Literally. It helps see farther, move faster, burn cleaner, heal more precisely. All this, from desert dust, from a place where heat reaches 110 degrees Fahrenheit, and wind sweeps away traces in a few minutes, as a symbol that even in the driest desert, the future can be born. Mountain Pass was once just a point on the map, the only mine of this type in all of North America. But now it's surrounded by an entire network of structures that transform crude ore into pure elements, ready for the most complex technologies, from electric motors to jet guidance systems. MP Materials Company has built here not just a mine, but a closed-cycle production, something America lost back in the 1990s when all supplies depended on China. After many years of research and investments in hundreds of millions of dollars, new lines operate almost without human participation. All processes are controlled by computers. Sensors measure compound purity, robotic cranes move containers, and special cameras capture every dust particle. Air in laboratories is so sterile that it feels like it's not a desert, but a space station. Everything that comes out of these shops is sent to other factories, which are also being built inside the country. In Texas and Ohio, they're building factories that will manufacture permanent magnets, precisely those that ensure the operation of Tesla electric motors, wind turbines, or fighter guidance systems. Once these magnets were supplied from China almost 100%. But now America plans to completely switch to its own materials by 2030. People who work here say they feel part of something bigger than just production. When they watch as a substance comes out of desert soil that will later turn into part of a satellite or a high-precision laser, it resembles a true miracle. Next to the quarry grow warehouses, laboratories, transport hubs, and on the horizon, also solar panels that power this giant. After the mine closed in 2002, when Chinese companies effectively monopolized the rare earth elements market, only a few dozen workers remained in the Mountain Pass area, maintaining security and basic infrastructure. The nearby settlement declined, stores closed, roads overgrew with weeds, and local families moved out to look for work. When in 2017, MP Materials Company bought out the assets and launched a modernization program, the situation began to change literally from scratch. Over several years, more than 800 jobs were created at the enterprise itself, not counting hundreds of related ones, in transport, chemical supply, technical service, energy, and even local services. In neighboring towns, cafes reopened, schools received funding, and roads, repairs. Besides direct vacancies, MP Materials launched a professional training program, cooperating with local colleges. Graduates of technical specialties can now do internships right at the modern processing plant, where they learn to work with automated lines, flotators, hydrocyclones, and chemical separation systems. Interestingly, jobs here are very diverse, from geologists, chemical engineers, process operators, to programmers and data analysts who control plant operations through digital panels. Each shift means tens of thousands of parameters read by sensors in real time. In a broader sense, the revival of Mountain Pass has become a symbol of the return of American manufacturing, which for decades was exported abroad. Against the background of political statements about reshoring and strengthening the internal supply chain, this project is often cited as proof that even in the desert, you can create a modern, profitable, and stable industry. Every year, the world mines over 900,000 tons of rare earth metals. Without them, not a single smartphone, electric car, or wind turbine would work. But there's one place where most of them are born. Bayon Obo, a massive quarry in the heart of China that supplies 70% of all the rare metals on the planet. Here, the earth glitters with metallic dust, and every dump truck hauls raw material for the future. But behind this shine hides a dark truth. Lakes of toxic waste, and the price nature pays for technological progress. Stick around till the end, and you'll discover how dust and poison create the foundation of modern civilization. The story of Bayon Obo started back in the 1920s, when geologists discovered a strange ore in this area, a mix of iron and minerals unknown at the time. In the 1950s, Chinese scientists realized that hidden here was a treasure trove of rare metals: neodymium, praseodymium, cerium, yttrium, and lanthanum. Since then, Bayon Obo has become the heart of China's strategy that would eventually turn the country into the undisputed leader of the global rare earth market. Every year, about 270,000 tons of rare earth concentrate are mined here, more than all other countries combined. It all starts simply. Massive dump trucks the height of a 2-story building pull up to the edge of the quarry, where giant excavators with buckets like a dinosaur's mouth rip out chunks of monzonite ore. Each bucket can hold over 100 tons. The dust rises in columns, and it feels like the very air here is saturated with metal. But extracting the ore is just the beginning. The real value is hidden in microscopic inclusions of rare earth minerals. Their share in the rock is only a few %, so after extraction, the ore is crushed and sent to processing plants, where a complex chemical story begins. First, the ore is ground to dust, then subjected to flotation, a process where particles suspended in water are separated using reagents. Rare earth particles stick to air bubbles, rise to the top, while the rest settles to the bottom. This is just the first step, because the concentrate still contains plenty of impurities: iron, calcium, fluorine. Next comes chemical extraction, which transforms the concentrate into high-purity oxides. This is an extremely complex process. In specialized reactors, the ore is treated with acids, usually sulfuric or hydrochloric, sometimes with the addition of fluoride compounds. After this, the resulting solution is separated into fractions using organic solvents. Each element, neodymium, praseodymium, cerium, has its own chemical quirks, so the process requires dozens of sequential cycles of extraction, precipitation, filtration, and drying. It's these oxides that then go into the production of permanent magnets, the main consumer of rare earth metals. For example, one iPhone might contain less than 1/10,000th of an ounce of neodymium in the speakers and vibration motor. In a modern wind turbine, nearly 1,400 pounds of this element. And here's the wow fact: just 1 gram of neodymium can provide a magnet for a turbine that generates electricity for roughly 1,000 homes. It sounds like an energy miracle, but it has a flip side. The problem is that chemical processing of rare earth ores is extremely toxic. Every gram of pure metal means tons of waste. In the Baotou area, near Bayon Obo, real waste lakes have formed. Black, acidic bodies of water where radioactive elements, fluorides, and heavy metals accumulate. They're visible even from satellite. Even with modern cleaning technologies, chemical processes leave their mark on the environment. Local residents tell stories that over the past decades, dust from the quarry and processing plants has changed the soil color, and grass around the area has been growing worse. However, the Chinese government is taking measures, implementing closed-loop water systems, controlling acidic runoff, and converting some facilities to new, green technologies, where instead of traditional acids, they use ionic solutions and membrane separation. All this is being done not just for environmental reasons, but also because China aims to maintain its dominance in the global rare earth metals market. Today, it accounts for 70% of global production and over 90% of finished oxide and magnet production. Other countries, the US, Australia, Vietnam, Malaysia, are trying to develop their own deposits, but they haven't come close to Chinese scales yet. Bayon Obo has become more than just a quarry. It's a symbol of the technological era, where Earth transforms into smartphones and ore becomes electric wind. Right here, among mountains of metallic dust, the elements that power digital civilization are born. There's a certain irony in this. In the quest to create a green future, humanity has become dependent on one of the dirtiest industries. Magnets for electric cars and turbines, batteries, solar panels. All of this requires metals extracted from places like Bayon Obo. And the greater the demand for clean energy grows, the deeper this giant wound in the earth becomes. Despite this, for China, Bayon Obo is a source of national pride. Thousands of people work here, and the territory itself is equipped with modern infrastructure, conveyor systems, automated drilling rigs, chemical plants that operate almost without human involvement. On the surface, sensors are installed that track air composition, and in reservoirs, pollution levels are monitored in real time. Every dump truck descending into the quarry is part of a giant machine that supplies the world with energy, data, and sound. And when we hold a lightweight smartphone in our hands, it's worth remembering that a piece of this device, maybe even that very magnet in the speaker, was once dust in the Mongolian desert. Neodymium is one of the most famous, and at the same time, most mysterious rare earth metals. It's a silvery white, shiny, fairly soft metal that easily oxidizes in air, so it's usually stored under a layer of oil, or in an inert atmosphere. Sounds unremarkable, but this element has become the quiet engine of the modern technological revolution. Without neodymium, wind turbines, electric cars, headphones, laptops, and even rockets wouldn't work. In pure form, neodymium doesn't have the magnetic properties it's valued for. They appear when it's combined with iron and boron, forming an alloy. This is the material used to make the most powerful permanent magnets on Earth. One neodymium magnet can hold weight hundreds of times its own. In industry, it's called a supermagnet, and for good reason. It's what makes compact electric motors, miniature speakers, and highly efficient generators possible. One study indicates that between 2001 and 2021, Bayon Obo supplied about 60% of neodymium from China's total neodymium extraction. On one hand, Bayon Obo is a remote, harsh, and dusty place. On the other, it evokes an almost magnetic curiosity in those who want to see what modern civilization looks like in its raw material form. Bayon Obo today is not just a mine, but an entire complex with its own small town, a rare earth elements museum, and even a special viewing platform from which you can see the giant pit going hundreds of feet deep. The flow of tourists here is small by Chinese standards, but steady. These are mainly engineers, geology students, bloggers, eco-tourists, and those fascinated by industrial landscapes. In 2019, local authorities even declared Bayon Obo part of the Industrial Heritage of Inner Mongolia route to show how mining and processing have transformed the region. In tourist brochures, this place is called the heart of the rare earth planet. The road to the quarry leads through endless plains and low hills, where the wind almost never stops. The air carries the smell of metal, and from a distance, the quarry looks like a giant amphitheater, where Earth plays the starring role. Tourists aren't allowed close to the mining zone. It's too dangerous, but there are several safe spots from which you can take photos. The most striking moment is when quarry dump trucks slowly move at the bottom of the pit. They look like toys. The scale is so massive. They extract it in mountains where stone is born from flames and pressure capable of crushing anything alive. Its formation takes hundreds of millions of years, and today, people cut it with diamonds at a speed of 20 miles per hour. But what if I told you that this shiny material, used to decorate palaces and statues, was once the bottom of an ancient ocean? And that every slab of marble is a frozen story of life, death, and time. Watch until the end, and you will see how nature creates its own masterpiece, and people try to uncover its secret. Marble is not just a beautiful stone for decoration or sculpture. It is a material that has millions of years of geological transformation behind it. Its journey begins deep underground, where temperature and pressure change ordinary rocks beyond recognition. The basis of most marble is limestone, a sedimentary rock formed mainly from calcite. Limestone is formed at the bottom of ancient seas and oceans from the remains of marine organisms, corals, mollusks, foraminifera. Over millions of years, these fragments settle, compact, and cement together under pressure to form thick layers. When such layers fall into a zone of tectonic processes, where the Earth's crust moves, compresses, or subsides, they sink into deeper layers of the Earth. There, the temperature can exceed 1,200 degrees Fahrenheit, and the pressure reaches 1,000 atmospheres. Under these conditions, metamorphism begins, the process of transforming rocks without complete melting, but with a change in their structure. During metamorphism, the calcite crystals in the limestone begin to recrystallize. The old grains disappear, and instead, new ones grow, larger, tightly fused together. This process gradually transforms the loose sedimentary rock into a solid monolith with a characteristic shine and granular texture. It is this structure that gives marble its famous ability to be polished. The variety of colors and patterns in marble is the result of impurities that got into the limestone during its formation or metamorphism. If there is iron in the rock, the marble acquires reddish or yellow hues. Graphite or organic matter makes it gray or black. Impurities of serpentinite or chlorite add green tones. Quartz, dolomite, and pyrite create veins, the same patterns that make marble seem alive. Marble is not formed instantly. The process can take hundreds of millions of years. In places where tectonic plates collide, for example, in the Himalayas, the Alps, or the Apennine Peninsula, the rocks experience the most intense pressure. That is why such areas have become world centers for marble quarrying. For example, Carrara in Italy, where white marble of extraordinary purity was formed. During metamorphism, degassing also occurs, the release of carbon dioxide that remained in the pores of the limestone. Because of this, the structure of marble becomes almost non-porous. This density makes it durable, but also more brittle with sudden changes in temperature. In some cases, the process of marble formation can be partially reversible. If the temperature is too high, the calcite begins to melt, forming intermediate forms between metamorphic and igneous rocks. Such transitional marbles are found in areas of contact between limestone and magmatic intrusions, for example, near granite massifs. Another interesting feature is the zonation of formation. In nature, it is rare for an entire layer of marble to have the same structure. In different areas, the pressure and temperature are different, so some layers are coarse-grained, others are fine-grained, some have veins, others have a uniform color. This explains why even within a single quarry, marble of a completely different appearance can be extracted. When geologists study deposits, they are looking for precisely those places where the limestone has undergone complete metamorphism, but has not been destroyed by excess heat or deformation. Sometimes these layers lie at a depth of several hundred feet. Sometimes they come right to the surface, as in Tuscany or Greece. The quarrying and processing of marble is no less fascinating a process than its formation. The modern marble industry combines powerful machinery, precise laser technologies, and artisanal craftsmanship that has barely changed since the time of Michelangelo. The first stage is the identification of the deposit. Geologists conduct research on mountain ranges using georadar, laser scanning, and drilling samples. The goal is to find a layer of marble of the required thickness, color, and uniformity. Sometimes the required layer lies almost on the surface, as in Carrara in Italy, or on the island of Paros in Greece. In other cases, it has to be uncovered, removing tens of feet of rock from above. When the site is prepared, the separation of marble blocks begins. Once, this was done with explosives, but now much more precise and safer methods are used. The main tool is diamond wire saws. This is a steel cable on which hundreds of diamond segments are strung. The cable is stretched between two pulleys and rotates at a speed of over 20 miles per hour, gradually cutting the stone like a string cuts cheese. Thanks to a water cooling system, the cut is even and smooth, without cracks. Another method is drilling vertical and horizontal holes in the rock, through which a diamond wire is then threaded. This forms the rectangular contour of the block. When the cuts are connected, a huge piece of marble, usually weighing from 20 to 50 tons, is separated from the mountain massif. It is propped up with hydraulic jacks, steel wedges are inserted, and the block is gradually released, preventing a sudden fall. Next, the blocks are transported from the quarry to processing plants. On the slopes of mountains, powerful tracked loaders and platforms on heavy trailers are often used for this. In mountainous areas where there are no roads, marble is sometimes lowered by special cable systems, a kind of funicular that leads from the quarry to the valley. In the workshops, the blocks are cut into slabs or blanks. For this, gang saws are used, large frame machines with dozens of steel blades, between which an abrasive mixture with water is fed. In modern production, they have been replaced by diamond circular saws or laser cutting machines. The cutting accuracy reaches fractions of a millimeter. After cutting, the surface of the slabs is ground with abrasive stones of different grits, gradually moving from rough grinding to mirror polishing. If the marble is intended for architectural projects, it is further strengthened. A thin layer of resin or fiberglass is applied to the backside. This prevents chipping during transportation and installation. For sculptures, such reinforcement is not done. On the contrary, they look for a stone with a uniform texture without microcracks. Polishing is a separate art. It is performed on large machines where a series of round abrasive discs pass over the surface, gradually giving it a deep shine. To achieve a perfect effect, powders of tin or cerium oxide are used. It is they who reveal the structure of calcite, and the marble begins to play with reflected light. After polishing, the marble slabs are marked and sorted by color, pattern, and quality. Part of it is sent for export, another part to workshops for carving, facing, or manufacturing architectural details. Sculptors work with marble much more delicately. They use hand chisels, hammers, and now, pneumatic tools that allow them to carefully remove the stone layer by layer. Even with modern technologies, the art of marble processing remains semi-artisanal. It requires an eye, a touch, and an understanding of how the rock behaves. At the end, the marble products are coated with protective waxes or silicone impregnations, which enhance the shine and protect the surface from moisture. For interior work, softer compositions are used. For facades, water-repellent, UV-resistant ones. Quarries are usually located in mountainous areas that are difficult to reach. To cut blocks weighing from 20 to 50 tons, expensive equipment is needed. Diamond wires, cranes, hydraulic jacks. At the same time, about 30 or 40% of the quarried stone is suitable for commercial use. The rest is cracked or defective blocks that go to waste or are crushed into crumb. Due to the mass and fragility of the slabs, they are transported on special trailers or containers with cushioning. For imported marble, delivery can account for up to 30% of the final price. Every year, over 90 million tons of chemical fertilizers are produced worldwide, without which half of the planet's population would simply have nothing to eat. But how exactly are these granules, which nourish life on Earth, created? In the depths of giant underground mines, in reactors with a pressure of 5,000 pounds per square inch, and at a temperature of almost 900 degrees Fahrenheit, chemists transform gas, rock, and salt into something that becomes bread on our table. But behind this technological perfection lies a secret. A process that changed the course of history and at the same time put humanity at a risk that few people suspect. Watch until the end, and you will understand why these granules can be both a salvation and a threat. The production of chemical fertilizers is one of the most important industrial processes in the world, as it provides the key nutrients, nitrogen, phosphorus, and potassium, to support global food production. It is a complex, energy-intensive, and high-tech chain of chemical transformations that begins with the extraction of raw materials and ends with a granulated or liquid final product. Potash fertilizers, the source of which is potassium, are almost entirely made from natural deposits of potash salts, usually potassium chloride. The process does not require complex chemical reactions, as in the case of nitrogen or phosphorus, but is mostly a process of physical beneficiation. Potash ore is mined from underground deposits. The ore consists mainly of potassium chloride, table salt, and other minerals. After mining, the ore is crushed, and then the potash salt is separated from unwanted components. The main beneficiation methods include flotation and crystallization. Flotation involves mixing the crushed ore with water and special chemical reagents. The reagents selectively adhere to the particles of potassium chloride, and then the mixture is passed through a chamber where air is introduced. The potassium particles stick to the air bubbles and float to the surface, forming a foam that is collected. Crystallization, on the other hand, uses the difference in the solubility of salts with a change in temperature. The ore is dissolved in hot water, and upon cooling, potassium chloride crystallizes first, separating from other salts. The purified potassium chloride is dried and granulated to obtain a commercial product. If it is necessary to produce potassium sulfate, a fertilizer that is better suited for some crops sensitive to chlorine, potassium chloride can be chemically processed, for example, with sulfuric acid, although this method is more expensive. The production of nitrogen fertilizers, the largest group, is based on the synthesis of ammonia, which is a fundamental building block. This synthesis is almost entirely carried out by an industrial method known as the Haber-Bosch process. Nitrogen is obtained from ordinary air, and hydrogen is most often obtained from natural gas by steam reforming. The first step is the preparation of hydrogen. Methane reacts with superheated steam at a temperature of 1,400 to 1,600 degrees Fahrenheit and relatively high pressure, which leads to the formation of synthesis gas, a mixture of hydrogen and carbon monoxide. Then the carbon monoxide reacts with additional steam in a conversion reactor to produce even more hydrogen, converting carbon monoxide to carbon dioxide. After purification, which includes the removal of carbon dioxide and residual impurities, a high purity mixture of nitrogen and hydrogen in a 1:3 ratio is obtained. The Haber-Bosch process itself takes place in high-strength reactors, where the purified gases of nitrogen and hydrogen are passed over a catalyst, usually iron-based, at a temperature that typically ranges from 750 to 950 degrees Fahrenheit and at extremely high pressure, often from 2,000 to 5,000 pounds per square inch. The reaction, which shifts towards the formation of ammonia under high pressure, is exothermic. The ammonia that is formed is separated from the unreacted gases by cooling to a liquid state. The unreacted gases are returned to the process, which ensures high production efficiency. Liquid ammonia is either the final product or an intermediate raw material for obtaining other nitrogen fertilizers. For example, for the production of urea, liquid ammonia and carbon dioxide react under pressure and temperature, first forming ammonium carbamate, which is then dehydrated to the final urea. For the production of ammonium nitrate, ammonia is first oxidized to nitric acid, and then the nitric acid is neutralized with additional ammonia. The final products are often granulated or pressed into pellets for ease of storage and application on agricultural land. Phosphate fertilizers supply plants with phosphorus and usually begin with the mining of phosphate rock, which contains phosphorus in an insoluble form. To make phosphorus available to plants, the rock must be chemically processed, most often with sulfuric acid. The production of sulfuric acid, which is critically important, occurs by burning sulfur or pyrite to form sulfur dioxide, which is then oxidized to sulfur trioxide, and finally absorbed by water. The processing of phosphate rock occurs by the wet process. The crushed phosphate ore is treated with sulfuric acid in reactors. The main reaction converts insoluble calcium phosphate into water-soluble phosphoric acid, and an insoluble byproduct, calcium sulfate, known as gypsum. The gypsum is filtered and removed. ENG6. The resulting phosphoric acid, which has a low concentration, can be used to produce so-called single superphosphate by its direct interaction with additional phosphate rock. However, more often the acid is concentrated by evaporating water and then neutralized with ammonia. Neutralization leads to the formation of highly concentrated fertilizers, such as monoammonium phosphate or diammonium phosphate, which are among the most common phosphate compounds. Many modern fertilizers are complex, meaning they contain all three primary elements: nitrogen, phosphorus, and potassium. They are produced by mixing intermediate products in precisely defined proportions to achieve the desired formula. The mixing can be physical, meaning a simple mixing of granules of different fertilizers, or chemical, where all components are contained in one granule. Complex fertilizers are often subjected to granulation. At the initial stage, there is a precise dosing of all necessary components to achieve the desired nutrient formula. Dry powdered materials, and often liquid components, are fed into a mixer. Here, the raw material is thoroughly homogenized to ensure that each future granule will contain an identical balance of nutrients. This ensures uniform application, as the farmer can be sure that every square foot of the field will receive the required amount of nitrogen, phosphorus, and potassium. The mixed raw material enters the main apparatus, the granulator. In industry, two main types are common: drum granulators and pan granulators. A drum granulator is a large rotating cylinder installed at an angle. A binding agent, often water or steam, is added to the raw material, as well as heat. The rotation of the drum and the stickiness caused by moisture and heat cause the small particles of raw material to stick together and roll into granules. As the particles are coated with new layers of material, the granules increase in size. The heat supplied to the granulator, often in the range of 180 to 250 degrees Fahrenheit, not only promotes chemical reactions, but also evaporates part of the moisture, making the newly formed granules stronger. The granules coming out of the granulator are moist and not strong enough. To achieve the required hardness, they are sent to a large rotating dryer. There, hot air reduces the moisture content, usually to less than 1% by weight. This is a critical step, as excessive moisture will cause the fertilizer to cake during storage. After drying, the granules are cooled in a special cooler. Rapid cooling strengthens the granule structure and prepares it for final processing. The cooled granules pass through a system of screens that separates the perfectly sized granules from those that are too small or too large. Granules that are too large can be mechanically crushed. Particles that are too small and dust are returned to the mixing stage in the granulator, where they serve as seeds for the formation of new granules. This recycling cycle is the key to the high efficiency of the process and minimization of waste. The granules are calibrated to a precise range, for example, from 1/16 to 1/8 of an inch in diameter, which ensures their suitability for modern sewing equipment.